Hey there, future mathematicians! Are you ready to embark on a new adventure in the world of mathematics? Today we're diving into the fascinating world of vectors. Vectors are essential in many fields, from physics to engineering, and even in computer graphics. Don't worry, it's not as scary as it sounds. In fact, once you get the hang of it, you'll see vectors everywhere. Imagine you're describing how to get to your favorite ice cream shop. You need to give clear directions, right? You wouldn't just say, "It's 5 miles away." That wouldn't be very helpful. You'd say, "Go 5 miles north." Now that's much clearer and more useful. That, my friends, is a vector. It's a way to describe both how far and in which direction. A vector tells us two crucial things: magnitude and direction. These two components are what make vectors so powerful. Magnitude is just a fancy word for how much. So, in our ice cream adventure, the magnitude is 5 miles. It's the quantity or size of the vector. Direction, well, that's pretty self-explanatory. It tells us where to go, in this case, north. It's the orientation of the vector. Vectors are usually represented by arrows. These arrows help us visualize both the magnitude and direction. The length of the arrow shows the magnitude, and the direction the arrow points in, you guessed it, shows the direction. Pretty straightforward, right? Once you understand this, you'll start seeing vectors in everyday life, from navigation to sports and beyond. Vectors aren't just some abstract mathematical concept, they're everywhere. Think about playing a video game. When you move your character, their movement is controlled by vectors. The game uses vectors to figure out how far the character should move and in what direction. Or how about in physics? Imagine throwing a ball. The force you use to throw the ball can be represented by a vector. This vector would show how much force you used and the direction you threw the ball in. So far, we've mainly talked about vectors on a flat surface, like a map. But what about in 3D space? Well, it's the same idea, just with an extra dimension. Now, our vectors need to tell us how far to move in 3 directions: left, right, up, down, and forward, backward. Think of a drone flying. We can use vectors to describe its position in the air. We need to know its height, its distance from a starting point, and how far it is to the left or right of that starting point. 3 pieces of information, 3 dimensions. Section 4. Vector operations, addition and multiplication. In this section, we will explore how vectors can be manipulated using 2 fundamental operations: addition and multiplication. These operations are crucial for understanding how vectors work in various fields, from physics to computer graphics. Just like numbers, we can do math with vectors. Vectors are not just abstract concepts. They have practical applications in real-world scenarios. By learning how to add and multiply vectors, we can solve complex problems more efficiently. 2 common operations are vector addition and scalar multiplication. These operations allow us to combine vectors in meaningful ways and scale them to different magnitudes, which is essential for various calculations. Let's say you're walking 3 meters east and then 4 meters north. This scenario can be represented using vectors, where each leg of your journey is a separate vector. We can represent each leg of your journey with a vector. The first vector points east, and the second vector points north. By visualizing these vectors, we can better understand the overall movement. To find your final displacement, how far you are from where you started, we add those 2 vectors together. This process involves combining the magnitudes and directions of the vectors to get a resultant vector. Scalar multiplication is when we multiply a vector by a regular number, called a scalar. This operation changes the vector's magnitude without altering its direction, making it longer or shorter. This changes the magnitude of the vector, making it longer or shorter, but it keeps the direction the same. Scalar multiplication is useful in various applications, such as adjusting forces or scaling velocities. For example, if you double the force you use to throw that ball we talked about earlier, you're essentially multiplying the force vector by 2. This means the ball will travel further, demonstrating the practical impact of scalar multiplication. Section 5. Vectors, the foundation of 3D geometry. Understanding vectors is like having a superpower when it comes to 3D geometry. They allow us to navigate and manipulate the 3-dimensional world with precision and ease. Vectors help us describe points in 3D space, define lines and planes, and even create complex shapes. They are essential for understanding the spatial relationships between different objects. With vectors, we can calculate distances and angles, which are crucial for tasks ranging from simple measurements to advanced engineering projects. They're the building blocks for all sorts of cool stuff, like computer graphics, animation, and even robotics. Without vectors, many of the technologies we take for granted today wouldn't be possible. So, congrats on taking your first steps into the world of vectors. This journey will open up new horizons for you in both academic and professional fields. It might seem a little abstract at first, and you might find yourself puzzled by the complexity of the concepts. But trust me, with a little practice and perseverance, you'll start to see the beauty and utility of vectors. You'll be a vector master in no time, capable of solving complex problems and creating amazing 3D models. And who knows, maybe you'll even discover new and exciting ways to use vectors to change the world. The possibilities are endless when you have a solid understanding of 3D geometry and vectors.